we are getting back to what we have learned in lower year. We have learned about finding the area underneath the curve, right? In fact, when the topic was covered, I'm almost sure you have been told that the area underneath the curve is given by this expression. Various set of notes, various teachers, various authors or books, they will give you the explanation quite similarly. I mean that there's some differences, but it's better. And the bottom line is, you always start off with a small strip, and then you just extrapolate to cover the entire stretch of the area. And you recall that the idea here is for the small strip, the area is roughly, okay, I would prefer to write this as delta, actually I prefer to write it delta. Doesn't matter, it should be fx delta x, right? Delta x and dx, there's small difference, in meaning, right? Okay, so it ought to be delta x, right? So, if you want to find the area of a small strip, you realize that it is like this, and to find the area of an entire patch, the whole world knows is this, and guess what? What is to come within this sentence? Of course, it's a diagram. What can you picture in the diagram? You will know that it'll be the other way around. Okay? We are already accustomed to this, right? This concept of finding area bounded by a curve and the x-axis. In fact, I'm also quite sure that you know how to find the area bounded by the curve and the y-axis. The formula just change, just do a tick. It's integration of x dy, kind of thing, right? And this can confuse quite a few people, no? When you have one area on top, sorry, one curve on top and one curve below. Whether is it this case or this case or this case, right? Whether or not it is a case that both curves are above x-axis or both curves are below the x-axis, or one up and one down, you realize after some logical thinking, you realize that the same expression actually works. Some people who are not aware of this, right? They will painstakingly try to actually find area on top, then find area below, separate, then add them up. Or sometimes when it's a bit more convoluted, where the maybe the graph is not so plain simple. Maybe it's like that. Like that. Even like that, first graph, a bit part of it is above, part is below. Likewise, the second graph, part of it is above and part is below. Even that, as long as one curve is consistently above the other, lo and behold, I want you to know that this formula works. Okay, that is to find area bounded by curve, x-axis, bounded by curve, another curve, and so on. So I am sure if you were to talk about area in the other direction, let me say with the y-axis and the curve, I'm sure you just have to check the formula a bit, and then you get the same thing. Okay? Show of hands up. Who have already learned how to find volumes? Everybody, right? I just be sure. Yep. Yeah, to find volume. Okay. I mean, as in volume, when a curve, when a region is rotated about the x-axis, or regions rotated about y-axis. Okay, we come to that shortly. Okay, now this is actually the one I'm talking about. No, area divided by a curve. Still area again. Sorry, this is area. This area here, right, can be found in two ways. One way is the straightforward way. You got an area of the top curve minus area bounded by the bottom curve. So it's like the formula we have now, the fx minus gx, then dx. So this one way of seeing it. This is an easy way. Right? It's exactly what we talk about when we say fx minus gx. Right? The second way, okay, let's first way again, the calculation first way again. The calculation first way, I'm sure you understand, right? So called the method one. The calculation is a bit, overwhelming because the function involved is tangent inverse, but if it's other function, actually it's not that actually. So in any case, you understand that this is a case of fx minus gx kind of thing, right? What do you think is a second method going to be like? Let's hear from Deborah. Yeah. What do you think would the second method be like for this same question? Brilliant! Right. Method 1 is easy, and according to him, method 2 is easier. Is it the solution in notes, I hope? Are there, okay, all in the notes area? All. Okay, so both methods are given to you in your notes, and it's just a recap. Okay. Brain power. Okay. So in this question, right, the easier method 2 is done when you do it in the other direction, Okay. Let me ask you, have you all used integration to find volume? Of course, you all learn how to find volume. I asked the silly questions now. So now let me rephrase it. You have used integration to find volume before, right? Okay. So you have learned how to find volume when the region is rotated about the x and about the y-axis, right? Okay. And I'm very sure you all can imagine how the shape is like. Given the region, if it's rotated, I am very sure. I took the trouble to give you some pictures to let you recall your good old days. Right. If you have a rectangular region, this picture very nice. It's picked up from the book by Howard and Third. It's called Calculus. Very nice topic. I just love the book. So if you have a rectangular region, it's not in the notes I know, because I ended on like okay. But if you want, I can say this picture. Okay, no worries for it. So this picture, once you look at it, wow, it becomes crystal clear. The graphic is nice, the color is also very nice, and this book author even make it very shiny and then make it very realistic. It's not easy, Those who have to 3D animation, you know what I'm talking about. When you create your avatar and you put a lighting, it's very interesting. Okay, well, these three are quite easy to visualize. This fourth one, when you rotate about the x-axis, it's actually hollow in the center. Okay. Show you more graphics. Okay, like I'm saying, a picture tells 1,000 words. Okay, this one, if you want to make a nice container, if you create a function that is so nice, and you rotate about the x-axis, you get a nice shape. Okay, this can become, I guess, a drinking cup, special drinking cup. And it's very important for this to be flat, so that your cup can really stand upright. A bell. Okay, he sees the bell. Typically, the end point is pointed typically, but the fact that it's cut out like that, I think, is because they want to make it as a cup. So you can actually design your own cup with a very fanciful shape, and then ask people to make it for you, fabricate for you. That'd be interesting, right? Okay, guess, how does it look like if you rotate about the x-axis? What would the shape be like? Can you imagine? Okay, let's see. It'll be hollow in the center, right? This book is fantastic, seriously. The drawing is something I can't match. Very nice, right? Yeah. So it's hollow in the center. Instantly, it uses the delta technology. Right. So another picture to show you. This is nice also, right? This is rotated also about x-axis, and because this is a straight edge, you will realize that in the center, which is hollow, is actually a cone. Okay, nice graphics. Okay, I think I got some more to show you. Ta-da! Okay. This show you that if you are dot against the x-axis, you'll be solid again. If slice y-axis is y, if you slice away, you get something that's hollow. Right to the bottom of the top, because there's a small gap here, right? So you see the small gap here also, the hollow in the center. But of course, this cannot be used to contain water. Water, of course, will seep through, no? Okay. Then the next one. Okay, this shows you that rotation need not be always about the x nor the y. It can be rotated about another horizontal line. In this case, y equals -1. You get a shape that looks like this. Okay. Then to treat your eyes to a good feast. Okay, that's nice. Okay, let's see. Okay, this one is new to you, maybe new to you. This one may be new to you. You're going to stare very hard at this, play more carefully, and try to understand what this is trying to say. Okay, you want to imagine this action. The whole class, this is the equation of x squared plus y squared equals 1 is the equation of a circle. So you can imagine there's actually a circle here. And then from this circle, in part A, right, you want to produce semicircles. In this case, right, this semicircle is perpendicular. So for instance, right, for this edge here, I now produce a semicircle. You can see? And I do it throughout the whole interval from this point to this point. And lo and behold, the shape that you get is, okay, move on.
Wait, but if the cross section is perpendicular to like the x-axis.
To the x-axis.
It doesn't have to be like this, right? It can also be like this or like this.
Okay.
How do you know?
Okay, I understand what you're talking about. So Guban raised a good point of, he says, when comparing the x-axis, this shape could potentially be looking this way, that way. But Guban, in this question, like they say the base is this thingy. Using this circular thing as a base, you're only one direction. Okay. And then because the so-called diameter of the semicircle changes along, the semicircle will get from very short diameter to longer and longer, right to the middle. You get something that is the biggest. After they start to diminish again. And the consequence of this is that you get a shape that looks, I think it looks like a hemisphere. It looks like it. Okay. Huh? Potentially, yes. Potentially, yeah. Amirul is saying that he knows the formula for volume of a sphere, so in half it, you get the volume of this object. Okay. How about if that it is now a square, right? Square, okay. So you can imagine how the square will be like, as you move along the axis. This is only one of the sectional part of it. So the end result is you get a very pointed thing in the sample, and then you start to diminish back again. And lo and behold, you're going to learn how to find the volume of such an object as well. And then equilateral triangle. Okay. They may look complicated, but I want to assure you that actually the idea is similar. The idea, how does it work? You just imagine that This is say in a semicircle. If I give it a little bit of thickness, right? If I give a little thickness, it will look like a semicircular disc. So you find the volume of the semicircular disc with very, very small thickness, and then you perforate throughout the whole interval, you get the volume of the object. The idea is similar to what you would actually have imagined for a case of area and those volumes that you already know of. I hope you like this graphics. Okay, this is another one. This is very interesting, you know. This is a case where the base is okay. The cross section is a hexagon six-sided, so you produce an object that looks like this. Okay, so now that you have seen a lot of graphics, I'm sure you are now powered up to want to learn how we can go beyond those things we learned previously to now conquer not so hard thinking. Okay, how are we going to do it? Okay, can you now turn to your notes to word example 39? In the meantime, let me fire up this thinking. If you look with me to example 39, in example 39, it describes for you a region. And what about the region? The region is served as the base of this thinking. The shaded region, right, is the base of the solid, where each cross section perpendicular to x-axis is a square. So this region that you see here is on the xy plane. We are going to build a solid by producing squares that are perpendicular to the x-axis. Produce square, you know. Okay. Okay. I'm going to do a demo, and I hope I can do it right. It's not done by me. It's done by another teacher. Okay. 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 Oops. Okay. Murphy's law. No? I practice it before coming. No? Okay. 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 Small. Okay. It's not done by me. I must give credit to my colleague, Mrs. Liu. Mrs. Liu did it, you know. Yeah. So she says I must first and foremost click this beam and say show trace. I must click on this and say show trace, and I click on this and I say show trace, and this show trace, and then she created animation that we can actually view how the squares changes in size, and boom, quite cool, right? Okay, so we are talking about a solid that look like this. You know what I mean? That when the square changes in size as it move along the x-axis, you actually produce a solid. And now we want to try to find the volume of such a solid.
So it's like an apple slice shape.
Okay, how do we find the volume of such a thingy? So you imagine that say at this point x, I draw a line up. At this point x, I draw a line up. I come off, I go this way, and that's a square. Can you see? So can you tell me for an x, right, what would be the area of that square? What would be the area of the square? The area of the square is y times y. Agree or not? The area of the square is actually y times y, or y squared. Okay? Then, if I will give you a small thickness, if I will give you a small thickness like this, so this is a semicircle for a particular x. If I go this way and I come off the board and then give a small thickness, the small thickness has a thickness of delta x. Okay? What then is the volume of this small, squarish thingy? It will be y squared delta x. Okay? Which means the volume of that small thingy is equal to this. So this shape will look like this, or this shape will look, if I may draw for you, I'm not very artistic, not that good, but I'm sure you can imagine what I'm drawing. Okay, so your eyes must be focused and understand that from this edge here, I produce a square, and this square has dimension y by y, because square same length and breadth, and then the thickness is actually delta x. So the volume of this small slack, if I may just describe that way again, is actually this much. And then to find the total volume, the volume then becomes, if you take limits and do argument in the limit, eventually your formula will look like this for x ranging from 0 to pi. And then because y is actually what? Sine x. So this becomes like it. Okay. So the volume, if you will do it correctly, it becomes like this. Class, this is the working. Okay, is it there for you? Is there for you, right? So the working is like this because, as I told you, y squared times delta x, right? That's a small volume. Now you sum it over the entire interval for x. And then answer is pi over 2. Kiran and Bharati, just share a discussion, maybe I can help. Okay, you're good. You're good. Okay? So this is 39A, where you can see vividly how the thing is formed. How about 39B? In the case of 39B, it's the same kind of thing, except that now it is perpendicular to the y-axis and it is an equilateral triangle. So for 39B, the shape has the same base, which is a semicircle, but to form the complete solid, you are going to make use of equilateral triangle perpendicular to the y-axis. So you can imagine it cuts across from left to right. It cuts across from left to right. And then for the area of a triangle, right? For the area of a triangle, we all know, the whole world knows, the area of a triangle is half AB, half AB sine theta. Because it is equilateral triangle, the angle theta is always 60 degrees. So if you look carefully, right, this will give me the area of the so-called triangle, right? Triangle. And then you give a small thickness, the small thickness with delta y. So altogether, right, the volume of this, let me know. Okay, I'm trying to find slab, okay, triangular slab, okay, will be equal to the area of the triangle times delta y. But to this calculation, right, it's also simple because in this calculation, right, you're gonna ask yourself this question: what is m? What is m? For a given y, what then is your m? And your m turns out to be, okay, y is your m like this. the M is like this is because you have done some calculation here. Some calculation here. Okay, this one is for the area, right? This area is in terms of M, but between M and the variable Y, the relationship is like that. If this value Y is this number, let's hear from okay lah, John. John, why do you think N is like that? Because you see that if this is X value, right? This X value here to here is half of it, right now. You see, if this is the X value, right? Here to here is half of it. So 2 times of it will be this entire length. That's why the M is this. And we know the relationship between X and Y, and we now replace the X with sine inverse of Y. Because we have the equation that define that link up X and Y, and the equation is none other than Y is equal to sine X. So for the reason, X is now replaced as sine inverse 1. Now that you have everything, to find the volume of solid, right? It is the area of this thingy times delta Y. You see? The area times so-called the delta Y. And you sum up from 0 to 1 because Y runs from 0 to 1. That will give you the entire volume. And to this integration, we replace the M with this thingy. And then using the GDC, you get the answer. Okay, a way to help you remember things like this now. Yes, Kiran? Say again? Pi minus pi, yeah. Yes. Gosh, thank you, Kiran. Yeah, this time this should be pi. Should be pi. Okay? Okay, change. Oh, but we are testing alertness. Kiran, stop it. You're very alert. Class, please change to this pi again. I'm blind. Okay.
Wait, what pi?
Here, movement, this is pi, not 2 pi. Pi over pi over 2. Yep. It's nice, you will see the bright spot. One way to help you remember is like this now. Class, for this kind of question, always remember this thing now. If the cross-sectional area are perpendicular to the x-axis, right? If it is perpendicular to the x-axis, you want to remember, no? If it is perpendicular to the x-axis, it will be a dx. Okay? It will be a dx. If it is perpendicular to the y-axis, it will be a dy. So this way, remember, no? If the cross-sectional area are all perpendicular to the x-axis, it will be a dx, and then vice versa. And then you just have to find the area of the cross-section in terms of x eventually, and in terms of y eventually. Okay, that is 39B. Any objections? Okay, don't have. Okay, let me press on. Jia Hui, you're obviously very tired. It's okay, no? You want to sleep so I can let you have a good rest so that next lesson you'll be awake. Will it be better? Okay, for part C is, I think it's much easier. Part C is the usual. Part C is just, part C is just volume about the x-axis. You know what I mean? Part C is just volume over the x-axis, and then you do. Actually, I got more animation to show you, every part has an animation. Would you like to see the next animation? Okay, let's show you part C again. Let me close this first. Okay, don't save, so I can use it for next class. Okay, while I'm firing up part C, you want to read exactly what part C is like. and then understand the working, I'll just show you the animation. It takes a while to put out to find out the thingy. Okay. Okay, so I will just run that. I think this one's easier to see. Okay, let's see. Nice, right? The good thing about this software is it can rotate, you know. Cool, right? Yeah, the creation of Mrs. Liu is quite cool. GeoGebra is fantastic, no? They create things like this for students to learn from. Okay, so based on what you have understood previously, to find the volume when it's rotated about the x-axis, we have the nice formula. This nice formula, and then actually, part D is the hardest. Part D is actually hardest. Part D is actually the hardest. What about part D? Part D wants you to find the volume of the object when it is rotated about the. Okay, so let you read the thinking for the wall, and then try to comprehend what this question is trying to do. And as you read, you will recall something that happened at the start of the year. Something quite similar. Because when you try to find the volume rotated about the y-axis, you will know that actually there's a left-hand ground, there's a right-hand ground, there's a left-hand ground. This part of the ground and this part of the ground, they have slightly different definition. What's the slight difference? The right-hand graph is like this. The x2 is actually this. The right part of the graph, and the left part of the graph is like this. And then looking at the expression in the integration, okay, I am sure you'll go back and practice the integration and get it through, no? Okay, incidentally, I'd like to tell you that the same volume for y-axis. Okay, before I move on, so I hope you understand actually this question, right? Make use of the fact that you're taking the bigger volume minus a small volume. The volume due to the right hand of the graph minus the volume due to the left hand. Okay. Right. There is this other way of going about it. There's this other way of going about it. For the same question, right? There's this other way to go about it. Okay. For the same volume, x only from 0 to pi, not 0 to 1. I'm trying to impress on you that the same volume could have been found. Y is sine x, right? I just want to show you that it can be found this way. Let me share with you how come the volume can be found this way. This is an alternative method, and it works very well for this question. Okay, why does it work so well? This other method thinks like this. No, it says for a given x, I imagine that this section of the graph is rotated about the y-axis. Okay, so it is rotated about the y-axis, right? It will form something like this. Okay, right. Given this line, if I rotate about the y-axis, it becomes something like this, where this one is exactly the x line. Okay. What do you think is the area of this cylinder looking thing? The surface area of this cylinder looking thing would be 2. Agree? Okay, because it's y. And now it has a certain thickness. If you got a slight thickness, imagine if now you got a slight thickness. Let me draw a thickness here again. Let me draw a thickness here. If it has a slight thickness, what then is the volume of that? If there's a slight thickness, right? Slight thickness, you have some volume, right? What do you think is the volume? Because if you were to slit open and roll it out, it's like a rectangular slab. So this volume will be roughly like that. Well, if you were to have a small thickness, this thing is going to be a cylinder with a small thickness. Well, you know what I mean? So if you slit it, and you roll it open, it's like a rectangular slab. And the volume of this rectangular slab is actually so-called area times the thickness. So this is the area and this is the thickness. So for the volume of the small thingy, okay, let me give a name to this. It's called a shell. It's like a shell. Okay, shell. They call it shell. It's not my creation. Like all you, I'm a good boy, and in the school days, I read up a lot. So I know there's this other method. Okay, some people call it the shell method. So the volume of this very thin cylinder-looking thing will be like this. And now, if you do it throughout the whole interval, to sum up all the shell, you get this nice-looking formula, which then can be done like this. Believe me, if you go through the integration by parts, very simple by parts. Don't take that long. You will still get the same answer as this. I'm illustrating this with you because this one offers you a very fast fix for the integration that you see there, which is harder because if you do it by hand. If you do it by hand, you can imagine, you just imagine to do it by hand. It's not easy. So that's why Mrs. Liu has resorted to the use of GC. And historically, it used to be in AP syllabus, this method. But somehow it was taken out, And the A-level students also don't learn this way, That is a loss. It's a loss, I say, knowledge. But luckily, you're here. You know what I mean? Even if you've not heard from them, you probably have read books, but just that because someone highlighted to you, you know there's such a thing, So years down the road, right, even if you don't remember entirely, you know there's such thing as this, You probably want to explore, Okay. And for today's lesson, it goes, after they've understood example 39, A, B, C, and D, we like to invite students to try now tutorial 3.3, question 5 and 6. And can you do question 5 on one side and question 6 on the other side? And you write your name, class, and date. And at the end of lessons, I want to collect back, not that I will mark all, I probably will not, but I want to archive this lesson with this as the practical. Okay. Let's jump to tutorial 5 and 6. Yeah, sorry, tutorial 3.3, question 5 and 6. I recorded the screen. Yeah, so people like him are not here, they're going to imagine that I was pointing. It's like that, you know. That's why on-site is of course a better learning platform, you know. On e-learning, you know, yeah. So some part has been discounted. So now everybody want to venture into question 5 and 6 of your tutorial. Sorry, like, what tutorial 2.3, question 5 and 6. Okay, 5 and 6. Okay. Okay, I'm going to shut down the recording because we don't need the recording for this part. You can make some noise first to make your presence felt.
Bye.
502, you make some noise. Bang the table. Okay. Yeah. Okay, let's see how do I shut this down. I need a F10.